I have two questions. One, how many of you have done the last homework problem? Well, yeah, in any case, I've received a few emails about it, so we'll talk about it briefly, probably at the end of class, just if nothing else for the benefit of the people who watch the videos at home. Other question is exactly where did we stop last time? What was the last thing you wrote down? Did we pose the question of when isogonal conjugates exist, or?
Oh, yeah.
But we didn't write the answer, did we? Or no? All right. So yeah, the question is, when do isogonal conjugates exist? And as we've seen, they can't exist on the sidelines because they're not defined on the sidelines. But where else? Well, they might not exist when the isogonal, or when you take your isogonal Chevians and you get three parallel lines, right? In that case, you don't have an isogonal conjugate either. So this first theorem provides a partial answer. It says if you take points on the circumcircle, then you always get isogonal Chevians, or parallel isogonal Chevians. So here's the theorem. Let X be a point other than A, B, or C on the circumcircle of triangle ABC. Then AX, BX, and CX are Chevians that are concurrent at X, and when you take their isogonals, you get parallel lines. So then the isogonal Chevians of AX, BX, and CX are parallel. So here's what we have. We have a circumcircle of some triangle, A, B, C. Let me actually draw this a bit more straight. I've drawn an acute triangle here. You always have to think about this. Doesn't matter if I have an obtuse angle. In this case, it doesn't. So this is really just one situation, but this covers all possible cases. And I'm going to choose a point X on the circumcircle. That's not one of the vertices of the triangle. And as you'll see as we go through this proof, it doesn't matter where I choose X to be either. So X is going to be either between A and B, B and C, or C and A. We'll just, without loss of generality, we'll assume it's between A and B. So without loss of generality, let X be on the circumcircle between A and B as shown. And obviously it doesn't matter which one I choose. If I chose between A and C, just relabel everything so it's between A and B again. And again, you might have to worry about, maybe there is some loss of generality if A is obtuse or something, but it really doesn't matter, I promise. Alright, so here's what I'm going to do. I'm going to draw on two lines in this picture. Well, hold on. Do I want to? Yeah, let's draw on two lines. So I'm going to construct a line coming from A and a line coming from B, where the angle that I construct here is going to be the same as this angle. So how about we call this angle alpha? Then I'm going to construct a line coming out this way that also has angle alpha there. And because I want to refer to this angle, say CA, let's give this point a name, some point on line Y. And the same thing with B. Let's call that angle there, let's call that angle beta. I'll construct a line coming out from B, say line BZ, where that angle is beta. Alright, so there's step 2. Draw lines AY and BZ as shown so that angle CAY is the same as angle XAB. I call it VAX in my notes, so this is in that order. Which will forevermore, we have to refer to this angle a few more times, so we'll just give it a name. How about alpha? And angle CBZ is the same as angle ABX, which is beta. Okay, well clearly then, looking at these angles here, clearly AY is a reflection of AX through the bisector of angle A, and BZ is a reflection of angle of BX through the bisector of angle B. So AY is the isogonal Chevian of AX, and BZ is the isogonal Chevian of BX. So clearly, AY and BZ are the isogonal Chevians of AX and BX, respectively. So what's the goal here? Well, the goal is we started with X on the circumcircle. We started with these two Chevians, AX and BX, and we constructed their isogonal Chevians. Our goal is to show that they're parallel, as it looks like from the picture. All right, so that's what we want to prove. We want to show AY and BZ are parallel. And I think just having the picture up here is enough to work with. I can erase everything else. Alright, so we'll just make a note. Obviously this is what we want to do. Our conclusion is going to be we want to show AY is parallel to BZ. We want to show AY parallel to BZ. And the way we're going to do this is really just with a whole bunch of angle chasing. We just need to make a bunch of angle sum arguments. So first thing I'll argue is alpha and beta, those are two angles in a triangle, so they relate to this angle x, right? Angle x would be 180 degrees minus alpha plus beta. So now, alpha plus beta, that's 180 degrees minus angle x. And 180 degrees minus angle x is another angle in this picture. What does that equal? what's true about opposite angles in inscribed quadrilaterals? They have to be supplementary, right? So 180 degrees minus angle x is angle C. Right, so this is because AXBC is an inscribed quadrilateral. Is that okay? All right, so let's do a bunch more angle chasing here. Hence, angle YAB plus angle ABZ. I want to break these apart into pieces. Angle YAB is the sum of two different angles, right? It's the sum of angle alpha plus this angle here, which I'm just going to call angle A. Do I want to call it angle A? Let's not be lazy. Let's call it angle CAB. So this is alpha plus angle CAB. The parentheses are redundant, but I think it helps illustrate the fact that that's the first term. Same thing with angle ABZ. Angle ABZ, I can break that into two pieces. Angle ABC plus CBZ. So angle ABC plus CBZ, but CBZ is beta. So what do we have? We've got angle CAB plus angle ABC plus alpha plus beta, but we just showed alpha plus beta is this angle of the triangle right here, angle C. What is the sum of those two angles? Or those three angles? What do those add up to? 180, right? It's all three angles of the triangle. It's angle C, A, and B. So this is 180. My claim is that that's enough, that we're pretty much done at this point. It's not the way I usually think of corresponding angles, but we've shown that this angle here and this angle here, I don't know why I did such a terrible job of labeling these things, those two angles are supplementary. So that means they're parallel. Why? Well, again, this isn't where I usually stop this argument, but think of continuing that on. If these two angles are supplementary, then this angle here is the same as this angle here. These are corresponding angles, so if they're equal, then this transversal is cutting through two parallel lines. Right, so this implies immediately that AY is parallel to BZ. Are we done? Technically not, right? The conclusion is supposed to be that all three isogonals are parallel. I've only done two of them. But now it's really easy to conclude that the third isogonal must be parallel as well. Why? Well, I start off with three concurrent Chebians, right? AX, Vx and Cx, those are concurrent. We had a big theorem last time that said that the isogonal Chevians are always either concurrent or parallel. Well, the isogonal Chevians can't be concurrent because I have two parallel lines here, so the third one has to be parallel as well. So finally, by the previous theorem, or I think we called it the corollary, by the previous corollary, it follows that the isogonal Chevian of Cx is also parallel. To AY and BZ. Does that make sense? Right, isogonals have to be either concurrent or parallel. Well, if two of them are parallel, the third one has to be as well. All right. So there is a partial answer. If you're on the circumcircle, then you don't have an isogonal conjugate because your isogonals are parallel. But it turns out those are the only points. And it's not hard to prove this, but I don't think we'll bother. So the converse is also true. Which means that, the only points in the plane giving rise to parallel isogonals are on the circumcircle. Again, it's important to think about and understand the logic here. We just proved if you're on the circumcircle, then you have parallel isogonals. But that doesn't necessarily mean that the only points with parallel isogonals are the ones on the circle. But if we have the converse that says that if you have parallel isogonals, then you must be on the circle, then that means, yes, the circumcircle is precisely the points that give rise to this type of situation. So let's draw some pictures. So hence, isogonal conjugates are defined for every point in the plane except the side lines of the triangle AB, AC, and BC. Remember here, I mean, take the line segments and extend them to infinite lines. And the circumcircle. So if we drew a picture of all these lines in the circumcircle, turns out you end up dividing the plane into 10 different regions. This divides the plane into into 10 distinct regions. 10 distinct regions as shown. I'll attempt to draw a picture. All right, so there's my triangle, ABC. I'm not going to label the sides because or the vertices because it'll start to look pretty cluttered. But there's ABC, and here's my circumcircle. And I do indeed have 10 different regions, right? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's label these as the textbook does. We'll call the inside W, inside the triangle, the interior. We'll call, really small writing here, we'll call that A, B, C. No, let me stick to my order. Doesn't really matter actually, but I'll call it ABC like that. And opposite this region A, we'll call this A prime. Opposite B, we'll call this B prime. Opposite C, we'll call this C prime. And then the last three regions, we'll just call them X, Y, and Z. And it turns out that this subdividing of the plane into these regions has this nice property, and that if I choose any point for one of these regions, then its isogonal conjugate is guaranteed to be in some other region. All right, so for example, I can't choose two different points in Y and have one isogonal conjugate end up in A prime and one end up in B prime or something. They would all end up in one of the other regions. So let's try and figure this out. Let's make a table. If X is in a particular region, and we have 10 of them, so we'll do W, A, B, C. A prime, B prime, C prime, and X, Y, and Z. All right, so a lot of these. Then where is its isogonal conjugate? Again, I'll use the notation from last time, X star, for the isogonal conjugate. Notation the textbook doesn't use, but I like it. Then where's X star? The first one's really easy. W. If X is in W, where's its isogonal conjugate? Yeah, if you're in the interior of the triangle and you take its isogonal conjugate, then you still end in the interior of the triangle. So that's something we don't really need to think about. You try this one though. Try putting it in A. So my picture's already too cluttered. I would recommend probably getting a scrap piece of paper or something, because it's gonna become fairly messy. But if I take a point, say X, lying down there, don't put the label there. If I just, I'm not even going to label it because it would be too messy. Put a point there. So that gives me 3 Chevians intersecting at X. Take the isogonal conjugate to those 3, just roughly, try and sketch it, and figure out where X star must live. this is you reflect those Chevians through the angle bisectors. So this first Chevian, the only interior one that I have here, if I reflected through this angle bisector, I would get something like this. And remember that even though I tend to only draw the portion of the Chevian that sort of goes from the vertex to the point we're looking at, Chevians are technically infinite lines, right? So this reflected Chevian, this isogonal, also extends off that way. And the reason I have to draw that is because that's actually where they're going to intersect. Take this Chevian now, reflect it through this angle bisector, and I'm going to get a line that does something like that, and also extends this way. And lastly, take this Chevian, reflect it through this angle bisector, I'm going to get something like this, and also extends that way. So where do they intersect? Well, they intersect out here in this region that I call it, if this was A, I call this region A prime. Hence the naming scheme, they're closely related. So if I take the isogonal Chevian of a point in, or sorry, the isogonal conjugate of a point in A, we get a point in A prime. Do you believe me? Again, far from a proof, just a sketch of thinking about what happens. And I promise you that that's true for any point in this portion of the circumcircle, or inside of the circle, but outside of the interior of the triangle. Obviously, there's nothing special about A. The same would be true for B and C. B and C. So if you're in B, take the isogonal conjugate, you land in B prime. C, you land in C prime. And also, we haven't stated this exactly so far, but obviously this isogonal conjugation stuff is a symmetric relation. Right, what I mean by that is if you take the isogonal conjugate of the isogonal conjugate, you end up back at where you started. Right? Reflect the Chevians and reflect back, you end up back where you started. So if I take a point in A prime and look at its isogonal conjugate, that's going to be back here again. So points in A prime end up in A, B, and C. And now we just need to play this game one more time for X, Y, and Z. So I think I call this region X. It doesn't really matter. We'll just take a point in this region. My advice to you is to try and exaggerate things a little bit. Maybe take your point, I don't know, kind of close to one of the boundaries. Maybe call that X. So you get these three Chevians. And once again, as before, just reflect them. Reflect them through the angle bisectors and see what happens. What'd you get, Adam?
Is it the same region?
Yeah, should be. And if I reflect this Chevian, the interior one again, you get a Chevian that looks like this. Again, it extends this way, but I'm not going to need this part, so I'm not going to draw it. Take this Chevian and reflect it. Okay, so I get something like this. But in order to intersect this line, I'm going to have to extend it this way. And again, how am I drawing these? I'm just drawing these so that this angle here is the same as this angle here. And then last but not least, take this Chevian. Well, this Chevian is really the way I think about this. If I were to just draw the Chevian itself, I'd probably draw this portion of it where it intersects this side. So if I reflect this guy, it's a little bit too steep to hit this, but if I reflect this angle over here, you get something that looks roughly like that. So there is the orthogonal conjugate. These angles don't quite work out for this one, but hard to draw this stuff by hand. So anyway, if you start off with a point in X and you take its orthogonal conjugate, it lands back in the same region in X. Same thing with Y and Z, nothing special about choosing X here. They're sort of symmetrically the same. But that's all we'll say about that. Isogonal conjugates, just isogonals in general, are a really big deal. Lots of cool stuff we could prove there, lots of cool stuff we could show, but we'll leave it alone. How long do we have? 15 minutes? One thing I'll ask you to do for homework is show that, what do we have? We had the symmedian point, right? We had the symmedian point, that is the isogonal conjugate of the centroid. So those are isogonal conjugates. Turns out that the orthocenter, and I think I mentioned this last time, the orthocenter and the circumcenter are also isogonal conjugates. I think I'll ask you to prove that for homework. It's fairly tough. So I think I'll probably only do 3 problems this week. But yeah, I'll ask you to prove that for homework. And something else you could show, this is difficult, and we won't talk about this, but here's, for example, a really cool result is, what's a pedal triangle? A pedal triangle, the actual definition, I mentioned this at the time, our textbook calls the orthic triangle the pedal triangle, but it's not the pedal triangle, it's a pedal triangle. Pedal triangle of point P is you go to the point P and you drop perpendiculars to all 3 sides from it. All right, that gives me 3 points, and the triangle connecting those 3 points is the pedal triangle of this point P. All right, so the pedal triangle for the orthocenter is the orthic triangle. So it turns out this is true. It turns out that if you take a point P and its isogonal conjugate, and you build the pedal triangles for both of them. All right, so build the pedal triangles for both of them. Alright, so I take a point and it's isogonal conjugate, and I build the pedal triangles for both of them. It turns out it's always true that these 2 triangles I wasn't expecting you guys to take notes on this, so my drawings are terrible. But it turns out that if you take the pedal triangles for both of those isogonal conjugate pairs, they both always have the same circumcircle. Which means our proof of the existence of the 9-point circle is just a special case of this. Right? The 9-point circle is formed when you take O And, did we do it for O and H? We did do it for O and H, right? Yeah, we did it for O and H. I'm just trying to remember our definition, because of course the centroid also lies on there. All right, so the 9-point circle is the circumcircle of the petal triangles for O and H, the orthic triangle and it is the centroid, O and G, right? It's the medial triangle. We proved that the medial triangle and the orthic triangle have the same circumcircle, but that's only because, damn it. Now it's not a special case anymore. I want to talk about O and H. Oh, that's the problem, G and H. There we go. No. Why am I getting confused? Yes, the petal triangle of the circumcircle, thank you. The petal triangle of the circumcircle is the petal triangle of the circumcenter is the medial triangle. Sorry, I had to think about that for a second. So in any case, they're isogonal conjugate pairs, and by this more general theorem that says this always happens for petal triangles of isogonal conjugate pairs, they have the same circumcircle, which in this case is the 9-point circle. So there's lots of cool stuff we can prove. We won't use any of that. In fact, we're going in a completely different direction for the rest of the semester, so I don't think we'll use any of this stuff ever again. But lots of cool things you can do. So anyway, I promised to talk about one of the homework problems. Which one was it? It was the last one. 4B.3. Here's the situation. All right, I have a triangle A, B, C, and I have a CR and BQ. So I have these three Chevians. Here's CR. We've got BQ, which cuts through CR at this point T, and we've got AT, which is sort of this generalized Chevian, this weird case where AT is parallel to BC. All right, so by generalized Cheva, we have, take the Chevian product, it should equal 1 because they're all concurrent at this point T. So we have AT over TB, or sorry, oh sorry, it's AR. AR over RB. Times BP over PC, but P is just point out infinity, so remember we just take that definition, we define BP over PC to equal 1. So times 1 times CQ over QA, this should equal 1. What we want to do is prove this equality without using Cheva. If you think about the things, if you think about everything in the right way, this isn't hard to do. Maybe there's other proofs out there with proofs involving area or something that don't look anything at all like mine, but here's one way you could do it, which is, well, for starters, I'm not going to prove that this times this equals 1. I'm going to show an an equivalent statement. I'm going to show AR over RB is equal to QA over CQ. And looking at a statement like that, I'm immediately thinking similar triangles, stuff along those lines, because it looks like ratios of sides and whatnot. Moreover, this picture immediately speaks to me. I see a big triangle with a parallel line cutting through it that's parallel to the base here, to BC. So I'm immediately thinking, let's try to use our lemma, right? So by the big lemma, whatever number it was in the book, I know RA, which actually, I'd usually call this RA, but we've got AR, so let me call it AR. AR over RB is equal to RT over TC.
RC.
Yeah, RC, thank you. It is. It's the shorter side over the whole thing. You get so used to doing Chevian products that now you're anyway. Yeah, it's over RC. Okay, so that's by our big lemma. Maybe I should just point out that it's only going to refer to this equality because I'm going to keep going. RT over RC. What else is this showing? Well, it really means that this triangle is similar. The smaller triangle here, RAT, is similar to the big triangle, RBC. Right? Because two sides are in the same proportion, and of course they share that angle. So by SAS they're similar, and that means that not only is the proportion of this side to this side the same as this side to this side, but AT is in the same proportion to BC. So that's the same as AT over BC. Again, you'll have to argue all this stuff, you'll have to write down the details, but it's pretty much what I just said. And my last claim then, is this. So we've got this to this. And my last claim is that this triangle here, QAT, is similar to this triangle QBC. Right, so triangle QAT is similar to triangle actually it'd be QCB. This you'd have to prove, but if you can prove that, then what do you have? Then I have that QA, AT is in the same proportion to BC as QA is to QC. So that would be equal to QA over QC or CQ. And then you're done. And you've established your result. So this is pretty much the entire problem. All you have to do now is write up the details nicely, and I think prove that. All right, we'll stop here. I'll see you guys next week. Remember, exam 2 is 2 weeks from today.